Today my name is Jason de Abrogar. I'm going to tackle about transmission losses. So first, transmission losses in any satellite's transmission, there are always losses from various sources. Some of those losses may be constant, others are dependent of statistical data, and others vary with the weather conditions, especially with rain. These are the types of losses: propagation losses and local losses. So, propagation losses when the light propagates in a transparent medium. Some of its optical power may be lost due to absorption or scattering. So next, local losses. These effects refer to the proximity of the local ground stations, possible sources that may interfere with the received signal, and buildings that may block the signal. These losses refer to loss of signal quality in each ground station. As you can see in the graph, that is losses of propagation. So next, these are three major issues to take into account as far as propagation loss is concerned: free space losses, atmospheric losses, and pointing losses. So from free space losses, free space loss is the dominant component in the loss of strength of the signal. It doesn't refer to attenuation of signals, but to its spreading through space. In order to perform all the mandatory calculation on the link power budget for any satellite, and key component must be taken into account: the equivalent isotropic radiated power, or EIRP, which may be considered the input power in one end of the link. EIRP is also introduced precisely at the beginning of all calculations, so it can be understood the source of each component and to allow the correct comprehension of all deduction presented. So next, atmospheric losses. This kind of losses derives from the absorption of energy by atmospheric gases. They can assume two different types: atmospheric authentication and atmospheric absorption. The major distinguishing factor between them is their origin. Attenuation is weather related, while absorption comes in clearly sky conditions. Likewise, these losses can be due to ionospheric, tropospheric, and their local effects. Next, ionospheric effects. All radio waves transmitted by satellites to the Earth, or vice versa, must pass through the ionosphere, the highest layer of the atmosphere, which contain ionized particles, especially due to the action of sun's radiation. Free electrons are distributed in layers, and clouds of electrons may be formed, originating what is known as traveling ionospheric disturbance. What provoke signal fluctuations, they're only treated as statistical data. The effects are polarization rotation, scintillation effects, absorption, variation in the direction of arrival, propagation delay, dispersion, and frequency change. These effects decrease usually with the increase of the square of the frequency, and most serious ones in satellite communication are the polarization rotation and the scintillation effects, and those are the ones that will be treated in this dissertation. So we'll go to polarization rotation. Polarization rotation: when a radio wave passes through the ionosphere, it contacts the layer of ionized electrons that move according to the Earth's magnetic field. The direction these electrons move will no longer be parallel to the electric field of the wave, and therefore the polarization is shifted in what is called Faraday rotation. This is not a serious problem in frequencies above 10 GHz. So next, scintillation effects. Scintillation effects. Difference in the atmospheric. Difference in the atmospheric refractive index may cause scattering and multipath effect due to different direction rays may take through the atmosphere. Difference in the atmospheric refractive index may cause scattering and multipath effect due to the different direction rays may take through the atmosphere. So we'll go to tropospheric effect. Troposphere is composed by miscellany of molecules of different compounds such as hail, raindrops, or other atmospheric gases. Radio waves that pass by troposphere will suffer their effects and will be scattered, depolarized, absorbed, and therefore attenuated. So we'll go to attenuation. As radio waves cross troposphere, radio frequency energy will be converted into thermal energy, and that attenuate signal. They will also be scattered into various directions, which means that there is a small percentage that doesn't reach the receiver antenna at the ground station. The main scatter particles in troposphere are hydrometeors like raindrops, hail, ice, fog, or clouds, and these particles represent a problem for frequencies higher than 10 GHz. Then rain attenuation. It makes no sense to determine the attenuation caused by rainfall because they will be very punctual events, since rain only causes severe attenuation in situation of heavy rain. Gas absorption. Under normal condition, only oxygen and water vapor have a significant contribution in absorption. Other atmospheric gases only become a problem in very dry air condition above 70 GHz. So we'll go to pointing losses. Ideal reception implies that the value for misalignment losses will be 0 dB, which means maximum gain at the ground station is achieved when both the transmitter and the receiver antennas are 100% aligned. Realistically, it is virtually impossible to achieve a perfect alignment between antennas of the ground station and the satellite, especially in the case of CubeSat due to their fast movement of nearly 8,000 ms1. So these are two ways for misalignment: off-axis loss at the satellite, off-axis loss at the GS. The first one is considered during the design of the satellite. The second type of misalignment is the antenna pointing loss that is usually quite small, not reaching even 1 dB, being the value a good approximation for pointing misalignment loss. Antenna misalignment losses AML are calculated using statistical data, so these values are an approximation based on real data observed in several GS. Ergo, these values are not calculated but estimated. So we'll go to equipment losses. The receiving of emitting equipment also introduce some losses to the signal. Feeder losses. Feeder losses occur in the several components between the receiving antenna and the receiver device, such as filters, couplers, and waveguides. These losses are similar to the ones which occur also in the emission between emitting antenna and the output of the high power amplifier, or HPA. So we'll go to environment losses. This item is related to the specific region of the globe where the ground station is placed: equatorial, tropical, and polar. Depending on its latitude, each region has its own characteristic: temperature, moisture, thickness of atmospheric ice layer, which may provoke variation in signal reception. Portugal has mid-latitude and is at a temperature northern region, which has no extreme values for atmospheric conditions. Hence, this factor may be neglected. So next, other impairments. There are also other factors that may condition satellites communications, even though that may have a mirror importance of CubeSats transmissions. They may become relevant in the other cases. So sun outage are punctual losses of communication between satellites and the Earth. Due to satellites' obscuration by the sun, it means that the ground station sees the sun behind the satellite with what is called a transit. It occurs in 5 or 6 days near the equinox and lasts for the maximum of 8 minutes each, in a total of 60 minutes per year. The noise temperature of the system becomes very high, and communications suffer negative consequences at about 100 minutes per year, or 0.02%. Sun outage affects other kinds of satellites but not LEOs. Satellite eclipse. This eclipse happens when the satellite crosses the cone of shadow of the Earth. They occur within 23 days before and after the equinox at March 21st and September 23rd. They last 70 minutes at their maximum and some strong thermal. Variations are produced during the eclipse. The satellite operates only with batteries and some transponders are disconnected. And that's all. Thank you. Goodbye.